Today I would like to present an untethered electro-pneumatic exosuit for gait assistance of people with foot drop. Many individuals live with an impairment that causes an irregular walking gait, characterized as slow, asymmetric, and inefficient, in which the individual would experience toe drag, high step page gait, and foot slap. Stroke, cerebral palsy, traumatic brain injury, and multiple sclerosis are some of the leading causes for this foot drop impairment. Exoskeleton can be a good solution for this. To solve this, we proposed an ankle exoskeleton, which is simple and inexpensive, with its major parts being 3D printed, and with pneumatic control electronics that can regulate vacuum and pressure for the system architecture components, as shown on the right. Our ankle exosuit has two major parts: actuation part and control part. For the actuation, it essentially has two circuits: the electrical circuit supplying power to the components for operation and control. The second part is the fluid circuit, defining the path of airflow to the soft origami. And on the picture at the right, the blue line indicates the electrical circuit and the gray arrow represent the airflow. The pneumatic actuation system has four operation modes. Position 1, actuated state of solenoid valve for vacuum. Position 2, normally closed state for compression. Position 3, static contraction. And position 4, static expansion. Here we show the front view and side view of the single valve assembly. The origami actuator is composed of stretchable 3D printed origami part as a skeleton and a nylon fabric skin wrapped around it. The two ends of the actuator are connected to the braces on wearer's shank and foot. Here is the mechanism of an origami actuator. Contraction is mainly driven by the tension force of the skin. The force is produced by the pressure differences between the internal and external fluid, and removing the fluid from the actuator will temporarily decrease the internal pressure. On the left shows a load test with varied forces. It indicates the outstanding performance of this type of actuator. The load can reach 300 Newton with 30 kilopascal, which is larger than normal pressure-driven method that produces no more than 60 Newton at 3 kilopascal. As for the control part, the control system consists of an Arduino Geo as microcontroller, a foot switch, and two relays, each connected to a separate solenoid valve. The foot switch sends signals to the microcontroller indicating which position the solenoid should shift to. The system can switch the positions of the solenoid independently, which gives us more options on how we can control the operation of the device. And here is the control diagram. Now we're showing a demo of this system. The toe strike will trigger the microcontroller to send a signal to the relays, turning on the vacuum. And heel strike will trigger the microcontroller to send a signal to switch the valve position, turning on the compression. So our exoskeleton has the novelties of portability, low cost, high force that allows it to help more people in need. In the future, the control algorithms will be developed to evaluate the assisted performance of the exoskeleton. Thank you.